You guys already know me, okay? I'm Nate. I oversee a lot of the electrical. James over here behind the computer is also, he's coming back. He was a student previously. He's coming back to help us with this as well. Today we're going to be talking about FRC electrical systems and controls. So all about like the electronics, diagnosing, common problems, things like that. So with that said, we're going to move on to the first slide. This is going to be some of our discussion topics today. So the first one is responsibilities of the electrical subteam. That way we understand what the responsibilities are of the subteam and understand kind of how to carry them out, because without a vision, you don't really know what you're aiming for. The next one is introduction to the FRC control system, the core components that make up the robot and the components that you'll use to wire the robot. Wiring and electrical etiquette, common problems, diagnosing, batteries. We have a whole slide on batteries and proper ways to care for them, common problems with batteries, things like that. The wiring standard for team 316, so our team. And then some closing remarks here. So we can move on to the first slide. So here's some of the responsibilities of the electrical subteam. So the first one is that we want to adhere to all the first robotics competition rules and regulations. That might sound simple, but surprisingly, a lot of teams every single season don't properly read the rules. Then they show up to a competition with either something illegal, the wrong wire size, and they end up having to redo a bunch of things. So we want to make sure that the first thing we do is make sure that anything we wire is legal to the standard of FRC. We want to make sure our responsibility is to make sure that we reliably power all the electronics during every competition match. So basically, our scope ends in electronics. So we make sure everything's running, everything's getting power. If something mechanical breaks, that's that's not in our scope, unfortunately. Like that would be on the mechanical team to have scope in. But our scope is to make sure that nothing electronically breaks, right? And so basically, if we can do our part, we know that the other teams will do their part, and then together we'll have a really nice working robot that's very consistent. So our goal is to make sure that we reliably power every single competition and don't have any issues there. Another responsibility is that we wire robustly. The robot goes through a lot of different things that are not common for like a standard wiring job. So something like, think of like an electrician wiring a house, right? The house isn't like shaking constantly or anything, right? But the robot is. The robot's driving on the field, it's smashing into other robots. So you have to wire a lot differently, and you have to fasten wires accordingly. You have to account for things like robot vibration, the environment, such as like driving, hitting walls, things like that. Linkages, parts that are rotating, chain that is rotating, moving pieces like an intake or something like that that's flipping in and out of the robot. And then you also have to keep in mind fastening your wires. So you want to make sure that you fasten them tight to different parts of the robot and that they're not going to be snagged on anything. The other responsibility is to create an electrical diagram. So then the programming team understands which wires are going to which motors, where different motors are located, how many motors we have on the robot, what motors we use, things like that. And then lastly, regularly upkeep and modify the wiring. So you want to wire in a way that allows you to modify it. If you have, like, for example, let's say you swap out an intake design, you want to be able to wire in a way that allows you to modify your wiring according to design changes and things like that. And you also want to make sure that there's room in your components that you don't have any problems like maintaining it. So like looking at different components, making sure everything's fastened correctly, things like that. So we can move on to the next slide. So why is electrical important? So here's some of the answers here. First one is it can allow you to win against anyone. So a lot of times, the nice benefit of electrical is that every team has it, right? Every team has an electronic system on their robot. And if yours is done really well and really robustly, then, and another team that might be, let's say they have a better robot than you, they might die on the field, and then it allows you to possibly gain an edge on the field, right, if it's a rough match. So there's been a few matches where our team has come out on top, even though we didn't think we were going to win a match, because the opposing alliance might have died from a hard hit on the field or something like that. So that's kind of where you can gain an advantage with electrical. Again, this is all about doing our part, right? So we can't worry about the other areas like programming and mechanical. On the electrical systems, we worry about our scope, and then we know that we trust that they're going to worry about their scope. It also allows us to employ new strategies. So something that we consider when we're running a robot on the field is different strategies that we're going to do for that match. So let's just have a scenario here where we'll say like our elevator is broken, right? And we're not going to fix it in time for the next match. So the plan is maybe our robot will play defense, right? And that might be a good strategy. Well, if our electrical system's not built very well, then we might die on the field when we're ramming into other teams and playing defense, right? I've seen that so many times where a robot goes over to play defense because something breaks and then they just die on the other side of the field. So having a strong, robust electrical system allows you to pretty much do any strategy that you want to do. So you can ram teams as hard as you want. You can block. You don't have to worry about dying on the field. And that's something nice that we have been doing year after year, is that we're not scared to go play defense, right? Some teams say we don't. Some teams we've talked to about playing defense, and they'll say things like, "Well, we're not sure if our robot's robust enough. It might break. It might die." We don't have that problem. It allows us to pretty much do anything we want on the field, whether we want to be scoring offense or if we want to be playing hard defense. It also allows us to aid alliance partners when we're working, consistently and we're not dying on the field. It allows us to tell our alliance partners exactly what we're able to do on the field, and then they're not going to have any unexpected things like us dying. It allows us to be more reliable for our partners. It also turns a good robot into a great robot. So if a robot is really good on the field and scoring a lot of points, but then they die occasionally, that might not be so great, right? Because they might die in the finals matches, they might die in an elimination match, and then the entire alliance is eliminated. However, if you have a consistent robot that's doing the same thing, your mechanical's robust, your programming's robust, and your electrical's robust, then over time, you're going to be doing the same thing every single match, and no one can really stop you, right? You're not dying on the field, you're not having anything break. It's kind of like you have a smooth sailing straight to the finals, and then hopefully winning the event. And then lastly, it's the ideal partner at the World Championship. So if you die on the field, teams will likely not pick you because they know that you might cost them the entire World Championship. At that level of play, it's one of those things where you need to have a consistent robot, because if you don't, teams might just not pick you just because of that, right? You might be really good, but if you're dying on the field, you'll probably get passed up for someone that's a little more consistent. So here's an introduction of some of the major, what we call the control system. When you hear us talk about the control system of FRC, this is exactly what we're talking about. So you have two main categories. You have major components, which are there at the top, and then you have minor components, which are here on the bottom. This is kind of what your general wiring schematic might look like. This is posted on the first website, and this kind of gives us a guide of how we're supposed to wire everything, where everything goes together. Of course, you want to reference a game manual as well, not just this diagram, but overall, this gives a general foundation, more of a visual representation, and then you can go through the game manual to verify. So the major components up here are your power distribution hub, which is right here, your Robo-Rio, your radio, which is right here. It looks a little different nowadays, but it's black now. Your radio power module, which is right here, your main breaker, which is right here, and then your RSL light right here. So those are all major components. And what is a major component? So a major component is a component on the robot that is legally required. Your robot has to have it. So then you have minor components here, things such as motors, motor controllers, cameras, sensors, pneumatics, voltage regulator module, pneumatic control module, mini power module, limelight. Those are all extras, right? So your robot's not required to have any of these things. Do you need motors to drive? Yes. But can you go on the field without any motors on your robot? Technically, yes. It's not a requirement. You don't have to have motors. Even though you do need it to score points and drive on the field, major components are things that you are obligated to have. You must have them on your robot. Minor components are extras, things that will aid you in accomplishing the tasks. We can move on to the next slide here. All right, what is a minor component real quick? We're only 30 seconds past the slide. Does anyone know what a minor component is? What's up, Gavin?
Something that's not necessary, not something that aids with the object of the robot.
Yep.
That's not required by the FRC rules.
Exactly. Yep. It's something that aids the rest of the robot into scoring tasks, things like that. And Lucas, do you know what major components are? Yeah. What is a major component?
The Robo-Rio. Especially because in the pits, when I was in the pits for RoboCon, the Robo-Rio stopped working.
Yes. And you can't move at all, right? So major components are things that you must have on your robot, right? To pass inspection, you have to have a Robo-Rio. You have to have a power distribution board, right? You have to have those. Major components are things that are required. You have to have them. So now we're going to talk about the differences between CAN bus and power cables. So there's two primary differences types of cables. These are mainly the two that are most common that you'll see on the robot. So CAN bus, so spelled all caps. What CAN bus is it's identified by the yellow and green cables. You'll see them all over the robot. And what their responsibilities are is they are always displayed in the color of green and yellow, as mentioned. They transmit signal from the RoboRio to individual components. They're very thin and very fragile. They're daisy chained across components, and they act as a school bus type, like visualize it as a school bus where it makes multiple stops, right? So this is CAN bus, and you can see that, so this is what's called daisy chaining, where you connect, your motors are each connected together, right? It's not like you have one wire going from here to the RoboRio, one from here. This is daisy chaining, where they're all bouncing off at each other. And essentially what happens is the RoboRio will get a signal through your code that you guys have in programming. It'll then send the signal, and it'll bounce from different stops until it gets to the motor that you're trying to control. So it'll bounce through each one of these, and then once it reaches the motor that you're saying go forward or turn, then it will command that motor to turn, right? So it's just like a school bus.
That cross through electronic part, that's the second CAN bus?
Yes.
We don't use that.
So we don't use this this year. We actually might, possibly next year. We'll see. But this is called, yeah. So this is called, I believe it's called the Canivore, if I remember correctly. And what this does is typically with your CAN bus, right, the yellow and green signals, what happens is if you splice this cable here and you get a cut in it, in your CAN line, the bus can't continue passing signal. So basically you're going to be completely dead on the field. You won't be able to control anything at all. So what the canifier does is it allows you to have two separate lines. So then you can have one that goes to, say, your drive motors, and then one that goes to the rest of the control system. And then that way, if one of them gets cut, let's say our elevator line gets cut, it doesn't shut the entire robot down, you can still drive. So the Canivore allows you to have two different chains of CAN bus. So then it's a little more robust. We haven't actually used that in the past, but we possibly will use it this year. So what are power cables? So power cables are always displayed in the color of red and black. Those are probably the ones you're a little more familiar with. They distribute power from the PDH, which is the power distribution hub, to individual components. And then they're generally a lot more rigid. So they might be like thicker cables. They're a lot more insulated, things like that. So your CAN bus are really fragile. If they rub on like a sharp edge, then it's possible that those will get cut very easily. Your power cables are generally a lot thicker, a little more robust. So here, we're gonna talk about some of our major components. So they're displayed here. So our power distribution hub, the PDH, that's right here on the left, or I'm sorry, my right, your left. And this is the RoboRio. Does anyone know what the power distribution hub does? All right, Ben, what do you got?
Distribution of power for that function of the motor at the work.
Kind of, similar. Does anyone else know? All right, what do you got, Ari?
I guess that it like delivers power directly from the battery, like to individual components.
So yeah, that's pretty close. So exactly right. So both of you guys had good answers. So the power distribution hub connects to the battery down here. These are where your big battery terminals go in. And then from there, it distributes power to all your different electronics through all these different channels. So it takes two little lines from your battery or two big cables, and then it splits it into like, I believe there's 20 channels. So it'll split it into 20 channels that then can go to things like motors, motor controllers, limelight, sensors, things like that, right? So basically it takes your small line and then it splits it. Does anyone know what the RoboRio does? All right, what do you got, Michael?
Controls the entire robot. It's the brain.
Okay. All right, that's pretty close, yeah.
Going off that, I'm gonna say it's the way that code is uploaded to the robot.
Okay, yeah, both of you guys had good answers. So the RoboRio is what the code actually goes on, like Michael and Gavin were saying here. And from there, that's where your commands are sent out from the RoboRio to all the different electronics. So this doesn't power anything as far as motors goes. It might power smaller sensors, but it doesn't power like large motors. It mainly just sends signal to the different motors and commands them on, it takes your code and then turns it, into action on the motors. So here a little bit, we'll talk about the power distribution hub. So this is, you can see your CAN line. So this is the end of your CAN line. Your CAN line starts at the RoboRio from here, then it runs through all your motors, and then it ends at the PDH right here. The PDH also has smaller things here, which are smaller channels for low voltage like electronics. So things like your radio will be powered from the PDH. If you have a pneumatic system, typically that's powered through there. And it also has a voltage display that'll kind of give you an initial impression of your battery. The RoboRio here has 3 different rails. So you have PWM, analog and relay, and the DIO. So these different rails have like low voltage supplies, so they can supply like power to smaller electronics. Things like our servo motors, where we activate the servo to climb, it drops the entire climb mechanism. Things like that are from the RoboRio. They're powered directly from the RoboRio. Those are low voltage, so it's not much load. And then some small sensors. So sometimes, like if you have a button sensor, that will be through the RoboRio as well. Okay, and I think we're ready to move on. So here's some other major components. So here's our radio. Does anyone know what the radio does? All right, Ben?
So it communicates to the RoboRio from the, so there's a station on the actual drive station that connects with the radio, sending the radio to code, and then the radio sends it to the RoboRio.
That's pretty close. So it doesn't, oh, go ahead, Lucas, you have something?
It just connects the computer to the robot.
Yes, that's a little more closer. So the difference, Ben, is something you mentioned, was that it sends the code through the radio. It doesn't send any code through the radio. So the radio is strictly to connect to the robot wirelessly, and then from there it does tap into your RoboRio, because that's how it connects to the control system. But no code goes to the radio, unless you're like pushing code, right? If you're deploying code, then it would go, your connection, it would send it through the connection down to the RoboRio. But like during a match, there's no code coming through there. This is the radio power module. It's pretty self-explanatory. It basically is the power line for your radio. So this is an adapter that you use that plugs into the radio and then connects that to the RoboRio. So your RoboRio goes from here to your, you have an Ethernet that goes from here to your RoboRio, and then an Ethernet that goes from here to your radio. And then this is where you run some power cables just to power that, and then it transmits it through. And what it does is actually inside, it has a split here. So it'll take your power, it'll send power through the radio side, but then it cuts power for the RoboRio. That way you don't accidentally send power backwards into the RoboRio. So it has like a little switch in there, is a way to visualize it. We can move on. We can move on. Oh, okay. So here's some other major components. So the main breaker is right here, and then your RSL light is right here. All right, so what's the main breaker do? Hopefully we know this. Oh my goodness. Okay. All right, Mike.
All power if too much power is on. That's what regular breakers do.
Kind of. Go ahead, Adi.
The on and off switch of the robot.
Okay, so that was a better answer. So it is like the on and off switch of the robot. So the reason it's called a main breaker is kind of what the reason Michael said, is because it actually is a breaker. So it's just like a breaker like you would see like in your breaker box at your house. Basically, Michael's correct in the sense that if you did draw an enormous amount of power, then it would actually automatically power off for a short period of time. So it'll shut off all the electronics. So that's kind of like a safety mechanism. It does act as a power switch for your robot, but it's also a safety mechanism. Let's say you had a major short on your robot, and it's so powerful enough where there might be a fire or a major safety issue going on. The main breaker hopefully will shut off the robot at that point. Now, if the fire's already started, it won't be able to do anything about that, but it hopefully will at least shut off the power to the robot to prevent it. What was I going to mention about the main breaker? I don't know. Yeah, so everything runs through the main breaker. So your battery ties directly into the main breaker and then through your PDH. So the reason the main breaker is directly connected to your battery is so when it shuts off everything, all the electronics. So does anyone know the difference between a fuse and a breaker? So you'll also hear the term fuse. Does anyone know those differences? What do you got, Lydia? Take a guess.
One, a fuse is like, it can't be undone, but a breaker, you can like resupply power.
Yes, so that's correct actually. So a fuse is basically, they're very similar. So a fuse is the same, where it has a certain power threshold, and when that power, if you go above that power threshold, it'll cut power. The thing with a fuse though is that has a line inside that'll break. Think of it as a bridge that will break if you go above that power limit. A fuse, once it breaks, it's done, right? It doesn't reset. It breaks internally. That's how they're built, and then it's just done. You have to replace the fuse, right? You can throw the old one in the trash. A breaker, on the other hand, just like your house, is when you go above the threshold, it'll shut off power, but then it'll, after a certain amount of time, usually about 30 seconds or so, it will reset and then turn it back on. So basically, like if you've ever tripped a breaker in your house, right, you usually go to the box and then you have to flick the switch and it'll reset your breaker. It's the same thing here. Now, if your house used all fuses, you would have to replace all those components one by one. So it wouldn't be as easy as just flicking a little lever. All right, and then what about the RSL light? Anyone that hasn't gone yet? All right, Locke.
Displays like the status of the robot, whether it's enabled or not.
Yep, exactly right. So RSL light displays the status of the robot. It's again another safety mechanism. So when programmers are coding or running teleop or autonomous tests or even on the field, it's a safety mechanism that allows everyone around to know when the robot's enabled, things like that, right? It also allows the field staff to know if it's enabled. That way they don't make sure they're reaching in the robot when the robot's already enabled, because then it could hurt them or it could activate a mechanism, things like that. So that's exactly what the RSL light is for. So here's some minor components. So hopefully you guys will know what motors do. What do motors do? Well, they do spin. What are they used for? All right, you guys can just call out. What are they used for? Yep, exactly. So they're used for powering mechanisms, right? So motors do spin, obviously. They're used for powering mechanisms, right? That, you know, you drive with them, you activate the elevator, you activate intakes. They power everything on your robot, right? Or what is a motor controller? So it is in the name. So a motor controller is kind of what you guys will be sending the command through your through the RoboRio to control the motor. So the motor in itself, if you have the motor plugged directly into the PDH, right? So let's say you have your motor directly in the PDH. When the motor gets signal, it's going to turn on full speed, right? It goes full speed forwards or full speed backwards. The motor controller allows you to have fine-tuning adjustments. So then that way you guys can code 10% power, you can code 50% power, you can make it go backwards 50%. That's what the motor controller does. It allows you to limit the power of your motor and also send signal to it. So it controls the motor, right? Now, a little difference here is this is what they used to look like. We still have some of these in the shop and we'll occasionally use them. They would be separate from your motor. So this would go before your motor, and then you would send the line to this, and then this would turn on the motor on and off, right? Now, in these motors, these are newer motors. These are called Krakens. These actually have an integrated motor controller, so they have these motor controllers in the back of them. They're integrated inside. So then you don't need a separate motor controller. Now, there are still some motors in today's age called Neos, and those still have a separate motor controller. You'll see them commonly on a lot of teams. A lot of teams have what's called a Neo. They look similar to Krakens a little bit, but then they have a separate motor controller that's white. So that's called a Spark. So then we use Krakens because we've just found them to be a lot more reliable. We like the way that they're interfaced with the code and the way that we can program them, and then also we like the all-in-one package with the integrated motor controller in the back. All right, lastly we have here a camera. So the cameras, I'm not even going to ask what does the camera do, but cameras basically allow, typically they're used to aid the driver, right? The cameras will typically be set up in a way that the drivers can use, they'll be set up at an angle that aids the driver in some way. So whether that means they're aimed at the floor where the driver could see the game pieces they're picking up. This year we tried to use it to be aimed at the climbers so then we can see the cage. It didn't work too well because that was like a quick job at the end of the season that we were doing, but typically they're used just to aid the driver. So here's some other minor components here. So what are sensors used for? All right, audio lock.
Getting feedbacks from the robot.
All right, anything else?
I was going to say, we use them a lot to detect whether or not we have game pieces in the robot.
Yep, exactly. So what'd you say?
What are the types of sensors?
Does anyone, name some types of sensors. Okay, beam brakes, yep. Travis, you have something? I saw you raise your hand, kind of. No other sensor?
There's more.
All right, what do you got, Gavin? Ultrasonic sensor, that's a sensor, yep. Anyone else have any other sensors?
Limelight sensor.
The limelight can be considered a sensor in a way, yeah.
Programmers, like what's the two different types of signals that a sensor will tell on a robot? From you.
What?
From you.
From me?
Yeah.
Say that again?
Like what are the two different types of signals that they'll be looking at? We have a lot of programmers.
Are you saying like the way they're... Right, so there's digital and analog types of sensors, right? So analog is kind of like, you can consider an analog like on or off, right? That's kind of like an analog. So think of it like a button, right? So there's button sensors that are considered. Basically when you press a button, it activates, it tells the programmers like do something, right? A lot of teams will use the button sensors too. They'll have an arm, and when the arm swings to the top, it'll press a button and then it'll tell the arm to stop moving, right? Things like that. That's called an analog sensor. So that's simple. It doesn't usually have any power going through. It's a simple switch that goes on and off that connects the signal together. On the other hand, then you have like digital sensors that a lot of times will be like more, they do take some power. So that might be something that's a little more active. So I wouldn't consider this a sensor, but like something like your servo motor sometimes will be like that takes power from the RoboRio. Or like I'm trying to think of a digital sensor would be something like the beam brake that Locke said.
I don't want to like correct you.
Oh, go ahead.
Digital on and off signals, analog is like on a gradient as far as input receive.
I might be getting them backwards here. I think, yeah, that's true.
Analog
Yeah, that's true. Okay, I'm probably getting them backwards. We haven't used the analog or digital in a long time, so that makes sense. Yeah, yeah.
And we don't use a ton, really.
We usually use through. Yeah, a lot of times we'll go through the PWM anyway.
Now.
I don't know if you've mentioned or not, but when
Yeah.
the RoboRio itself has some general purpose input output things
Yes.
that you can use to connect the
Yeah, but what that means
Sensor.
for the programmers is like on our drive controllers, we have potentiometers. Those will tell you like an amount of rotation.
Yes.
So that would be an analog input to your code. The digital input would be like our elevator button. It either is pressing or it's not. And that's just like a simple on and off. And they look different in programming. I learned Java.
So yeah, so RoboRio does have some inputs, and it will allow you to use sensors like that. It also has what's called a PWM rail that'll let you run your servos off of that. So okay, what is the compressor system used for? A lot of our newer students probably won't even know this. We haven't had a compressor in a little while.
Is it for like filling up air tanks that pneumatics use?
Yep, so you actually can have what's called a pneumatic system on your robot. So a good way to think of a pneumatic system is if you think of like any construction equipment, like a backhoe where it has a bucket that swings up and down, it has a cylinder that moves that arm, right? And that's the exact same way that you can think of that we can build onto the robot. What? What's up? Well, no, but it's the same type of system, right? So that's hydraulic. That uses what's called, that uses hydraulic fluid, which is a liquid to push into the cylinder. But a pneumatic system uses air. So it's a little more safe. You're not going to leak fluid all over the floor. But that's the exact same way you can think of it on the robot, right? It has cylinders that go in and out that can move arms and stuff like that, but it pushes air through to accomplish that.
What would you say is more efficient, pneumatic or hydraulic?
Like, you mean efficient or strong? Because hydraulic is stronger.
Well, stronger.
Depends on what they use. The stronger the hydraulic.
Yeah. So now you can't use hydraulics on the FRC system mainly. But there's a lot of reasons you wouldn't be able to do that. But yeah, I mean, you can think of it this way, right? So when you use pneumatics, it's very common for teams to leak air, have holes in their system. Now imagine if you use liquid instead, right? You would be dripping liquid all over the ground everywhere you go, right? So it'd be very common. All right, so this is a VRM. So it's called voltage regulator module. So does anyone know what this is used for? This is a little more challenging. Okay, give me an example of what. Give me an example of what we might use this for.
To restrict the power flow?
Not exactly. It doesn't act as a restrictor, but what it does do is it kind of converts and allows you to power some smaller like 5-volt sensors or in some cases some smaller 12-volt items. So what it does is it'll go from your PDH, right? And it'll have multiple outputs on it. So you have 5-volt outputs and you have 12-volt outputs. So certain things that you might power that are low voltage, you can go through here rather than take a channel on your PDH, right? So like, for example, don't quote me on this, I forget, I haven't wired the Limelight in a little while. I feel like the Limelight might be a 5-volt, no, it's a 12-volt input. I'm sorry, the Limelight is a 12-volt input. Yeah, the Limelight is a 12-volt, but I believe there's like some sensors, like the beam brakes and stuff like that, those are pretty common to be 5 volts, so we might run those to the 5-volt rail here.
And we haven't used that.
No, I think we have one on the robot this year. We'd have to see I forget what it's used for because it's been a while, but it definitely is, useful in some cases. It depends. This is an optional component, so you don't have to have this. So you can go ahead to the next slide. So here's 3 other additional minor components. You have your pneumatic control module that controls your pneumatic system. If you have like the pneumatic system on your robot, that'll activate the cylinders. That's what you send your signal to. You have your mini power module. So think of this as the mini PDH, power distribution hub. So that thing that you powered all the motors off of, that's like this is a mini version of it for other electronics on the robot. So it's kind of like it goes alongside the VRM, but this is only 12 volts. So this will be 12 volts. So you might power things like your Limelights through that. Like especially if you have multiple Limelights, right? You would use this. You wouldn't want to take all those slots on your PDH. You would want to just use something like the mini power module. Some sensors would be powered off of that. And then you have your Limelight vision system, which the Limelight is used for the robot tracking. So more for our newer students, but the Limelight is a camera system that's integrated that allows, it's kind of like an all-in-one system, allows the programmers a lot easier access to like target the April tags on the field, to track certain objects and things like that. So the Limelight is a visual aid that helps with a lot of things. It has a nice user interface and software as well. And we use the Limelight almost every year. Okay. So wiring and electrical etiquette, all right? So, oh wait, go back. All right, so All right, so wiring and electrical etiquette. So tips and tricks for electrical etiquette is that your wire pair should be labeled in a diagram. You should have like a diagram that pretty much, it doesn't have to be like a CAD diagram, right? It can be just something simple that says, hey, motor 2 goes to PDH slot this, motor 3 goes to PDH slot this, etc. So you basically should have a diagram in some way that shows which slots different components are going to. You should also have, before you start running wires, you should understand a clear route from where your beginning point is and then your end point is going to be. So then before you start running them and zip tying everything, you should kind of have an idea of where you're going to route those wires. You really should make sure that your wires are fastened. A lot of times on this team, we use zip ties and mounting plates. Those will kind of allow us to fasten our wires to certain objects. That's kind of common for us. We use a lot of zip ties on the field and we've had really good success with that. So. You also want to make sure your electronics are labeled, so that might be using the label diagram, like the label printer, and printing like different numbers or different names for the electronics. So the programmers assign individual values called CAN IDs, like usually it's like a number like 1 through, I forget the max number, but then from there what you do is you should have those labels on your motors. That way if the programmers say something like, hey, CAN ID 3 went out and we can't control that motor. Yep, in the diagram. And then also your wire should be accessible to make repair and diagnosing as easy as possible. So here's human 1 with bad wire management, okay? And then you can see that when you clean things up, you fasten your cables. Here's some fasteners right here. Look how much nicer and neat it is. Like, how am I supposed to find any problems in this mess, right? But then when it's fastened, I can see all my wires. I can easily identify any potential options there. All right. Here's a little more practical view of what bad wire management looks like on a robot. So you have our electronics panel from 2016. This was, I would say, the old age of the team. And then we have our electronics panel from 2018. And you can see that obviously there's a lot of differences, right? This looks like the human with all the blood vessels and things like that all over the place. This looks like a much cleaner board. So if you think, when we had issues this year, we could not diagnose anything, right? Everything was just, we pretty much were dead. I would say we were dead over 40% of matches in this season. And we also couldn't fix any of the problems because all the electronics, like this is a motor controller, it's just floating there. It wasn't mounting, it would just shake around. There's a bunch of cables that got stuck in this gear chain here and the gear just ripped it, right? And there's a lot of rotating components in here too. So that made a big mess, right? And ripped things. 2018, a lot more clean. A lot more easier to diagnose. You can see that all our power wires are right here. Everything's kind of easy to access. And then we also have quick connectors on the end, so then we can easily pull different connectors out and power them back up.
Were you a student on the team in 2016, maybe?
So that was my first year, yes. So I was still learning things. I did not do any of the electronics in that year. So, well, yeah, we didn't even qualify for FMA champs. So that's what I'm saying. This was more the old gen of the team, right? So we learned from it, obviously, right? This was a mistake that shouldn't have ever happened to begin with. But from here, we obviously improved only 2 seasons later. And then from there, we're doing a lot better, right? We haven't died in an official competition capacity. We haven't died in about 3 years now, I think it's been. So like obviously we died at Ramp Riot or at RoboCon previously. That was an off-season event. We don't really Well, right. So we had shorts, but that's in the competition season. We're a lot more tedious. We upkeep the electronics, but it's the same thing as all the other components on the robot that they've just seen wear and tear and things like that. So again, like we haven't died in an official competition setting in a long time. So, all right. So here's some common problems we see on robots most often. So you have your loose battery terminals. So basically if the 2 terminals that come out of your batteries, the 2 cables, if you can grab a cable and rotate it back and forth, then you should not ever use that battery until that gets tightened, right? So that the reason is because that means it doesn't have a strong connection and there's a high value of what's called a resistance, which means that that battery just, you need to tighten it before using it, okay? Bad batteries are common to be put in the robot. Loose mainline connections, so that might be again where your main cables are coming from your battery or your PDH and that they're wiggling, they're not tight on all their connectors. Loose Wago connectors, you'll see what a Wago connector is on the next slide, I believe. Cut cables, so wires that are like cut and you don't notice it until after the match, something like that. Old components, so worn out electronics, so things like breakers, over time they wear out if you keep snapping the breaker. Things like that can end up, they should be replaced at a certain point. Or even like old electronic components, if they've, been abused, they might have, like junk in them, like the Robo Rio might have chips, things like that. Metal shavings in the primarily in the Robo Rio. We've seen that quite a bit recently. And then also copper exposure in your cable. So that if you see copper, it either means one of two things. So if you can see copper sticking out of one of your connectors, it either means A, the connector is loose, right? It pulled out of the connector, it's not fastened properly. Or B, the person did not, they stripped the wire too long and the connector's in, but then the wire is still sticking out of the connector, right? So you never want to see any copper sticking out of any of the connecting points on the robot. All right, so here's some of so when I said you can grab a battery terminal and you shouldn't be able to wiggle it, this is what I mean. You should be able to grab any of these spots on the battery and you should be able to tug pretty hard and it should not rotate, right? If it does, then that means you need to tighten it a little more and it definitely shouldn't go in the robot. Same thing here, these are your main connector points. So from here, this cable goes down and then this is the other end of that cable. So then it goes to your main breaker and then your PDH. If you can wiggle any of these, that's not good either, right? So, so this is the core of your robot. This is where all the power comes from. So if this has a loose connection, everything else will just like die on the field, or like you'll drain battery really bad. So now if you have something like a loose connection on a motor, that motor might not work, but everything else should still work, right? But on your main line, if you have a loose connection on the main line, your whole robot will just be destroyed. So for that match, at least until you figure it out. So here's what's called a Wago connector. So you've probably seen these in the shops. These have a lever that flips up and then you can insert the wire in and flip the lever down. So on the team, we do not use Wago connectors for competition setting, mainly because over time, the vibration, the cable becomes loose and then it can end up pulling out of the Wago connector. They're really good in like a quick setting. Like let's say we have a sliced cable and we really need to get on the field. Like we don't have any time to repair it or add a new connector. That's when you would throw a Wago connector on, right? That's like the only case, right? And then you would just swap it for a permanent connector afterwards. That's the only time we use Wago connectors. Or for like quick testing in the shop, like if we're building like a test board or testing a motor, we might use Wagos for a quick capacity. But we don't use any Wagos for a official competition use. Now, this is a little controversial in FRC because you will see a lot of teams that use the lever nuts for the lever Wago connectors on their robot all over the place. If they've used them successfully, that's good for them. We have not seen that sort of success with the Wago connector, so we just don't use them at all in official capacity. We use what's called Anderson power poles. So this is what an Anderson power pole will look like. It has a little lever here, a little contact. So you crimp this onto the cable and then it slides into a housing and then it has another half that would connect. And then you can pull apart the connection, you can do anything you want. These have been very reliable for us and that's what we use. So here's some other common problems that you'll see. So, oops, it looks like I forgot some words up there, but that's okay. So anyway, you'll see metal shavings in the Robo Rio. We had that at RoboCon. We had some metal shavings that shut down the whole Robo Rio. This is a good way that people protect their Robo Rios. They 3D print inserts that prevent a lot of shavings from going in. We're gonna work on that for this season. We've used tape in the past, but I think we're going to work on building some sort of connector that covers the slots a little better. I think we're going to build a custom case that goes in the Robo Rio or over top that blocks off a lot of these. From here, you also can see here is a common problem that we see. I'll see this all the time with robots. You see the copper right there. It's hard to see, but you see that the connector or the wire is not all the way in. And what's bad about this is, number one, it might not be plugged all the way in to begin with, so it might not even be having any power. The other problem is if you have two of those next to each other and they touch together, then that's what's called a short, and then that's going to either drain your battery, that's going to cause major issues on your robot. And obviously that function won't work either. So you never want to have anything like this. It's crazy that I'm telling you guys this because like if you guys were to go and just do a competition and explore the robots in there, you will see plenty of robots that have this kind of issue, or plenty of robots that use the Wago lever nuts. Things like that are extremely common to see on robots. So here's some diagnosing. So the first thing you want to do is you want to brainstorm what is happening. So a lot of times when you're in the pit and like something major is happening with the robot, right, electronically, it's easy to think of like, hey, it could be this, it could be that. What you really want to just take a step back and kind of understand, hey, what is actually going on here? And usually when you're a little calm and you think about this a little logically, it allows you to kind of find the issue a little faster. You then narrow down the faulty area. Use process of elimination. So obviously, like let's say a motor is not working, you're not going to go and check a different motor, right? Like that, there's no point. Or if like you're draining battery really quick, that's probably not an issue on any specific motor, right? If you're like dying instantly on the field, that's probably something on your main line, right? It's not going to be like an individual motor. think logically, like I said before. You also should understand how much time do I have, once you find the issue, how much time do I have to repair this issue? And can I fix it in time? Otherwise, if we're not going to have enough time, what can we do to get the robot out for the next match, at least temporarily? So in some cases in the season, we might not have time to repair a Robo Rio or swap something out. So we might do something like, we might like try our best to repair it internally with leaving it in there. Or like sometimes when you have an issue with a Robo Rio, you just want to swap them, right? You might not have time to swap them. So a lot of times what we might do is we might like use an air can to try to blow out the Robo Rio, blow out any metal chips that are in there. Or, and like I said, if we don't have enough time to repair a spliced cable, we might use the Wago connectors, and that might be a good temporary solution. And then lastly, try to fix the issue once you have a little bit once you're a little lax on time, where you have time to fix the issue. All right, let's see. So here's the slide on batteries. So I have an individual slide on batteries because of how common battery issues are. So give me one moment. So batteries should be tested annually on the battery analyzer. That's something that we're trying to do every meeting. We're trying to test one battery. It takes like 2 hours, so you can really only test one per meeting. Then they should be documented if it passes, if it doesn't. There's something called a battery beak. That's a component that probably many of you don't know. But basically what the battery beak does is a component that plugs into the battery, and it'll give you a good understanding if the battery is at least competition ready. Now, it doesn't mean that it doesn't have its flaws. It's not what's called a load tester. So it's not something that will tell you like long standing of the battery, like, hey, this battery is good to go. That's why you run it on your analyzer previously. But the battery beak should say, hey, this battery is not dead. Like it should at least hopefully last you a match, right? Like it's charged enough to last you a match.
Tells me it's at 100% charge. If I've had it for 10 years, that means an hour of time. If
Right.
I had it yesterday, it could mean like 2 days.
Right.
So the information we're not getting is how worn out that battery
Yes.
is. Battery beak's just telling us, hey, this is 100% charge to what it can currently do.
Exactly.
Purely a voltage reading?
It's not only voltage. It does apply a low load, but only like up to 20 amps. So it's not something that you can apply like a high load on a load test. It's not like a load tester, right? And we do that for every battery before it goes on the robot for a match. Battery lead should be tightened and not rotating. And I've said that 3 times now, and because of how important it is, again, this is a very common thing. You'll see teams being able to just rotate their batteries, and then they're dying in a match, and then they don't even think that's the issue, which is the craziest thing. Like, they'll be dying in a match, and then they'll put the battery to the side and think it's something in their robot, and it's not the robot, it's the battery. Batteries can become damaged if they're left off charge. Over time, this is called an AGM battery. Over time, what they do is the batteries can actually discharge if they're not put on charge, right? So a battery doesn't stay charged, just like your phone. If you leave it, off the charger for 3 weeks, right? It's not going to still be at 100% power. So just like that, the same thing happens to a battery where it'll discharge slowly if it's not on the charger. And when it becomes so low that it goes under a certain threshold, that battery can actually be damaged where it no longer can reach the full capacity anymore. So when we're not using it in competition, the batteries should always be like stored. When they're stored, they should always be stored on charge to help maintain the life of the battery. It's okay if it's like 1 day, right? Like we're traveling in the trailer or something. That they don't need to be powered for that. But it shouldn't be like months or anything like that where the batteries are left. And then I think there's one more point on that last slide. Batteries should never be lifted by the leads. So that's another common thing you'll see with people is like the battery will be tucked in the robot and they'll grab it by the wires, and that's how they'll lift it in and out of the robot. What that does is that can crack your battery. It's pretty common to see people crack their batteries from that, and then they'll leak. The other problem is it'll loosen your connection, right, over time, and then you'll get those loose cables that we talk about. So here's some of the wiring standard for our team. So the first thing that we do with wiring is we always remember that we're performing every task with excellence when wiring. So we don't skimp out on anything. We don't say like, hey, this is a temporary fix, we'll deal with this later. Unless it's like in a match, right, and we have to get out on the competition, then we'll deal with it after the match. But it's not something that in the workshop we're gonna say, hey, we'll deal with this later, right? We do it right the first time. We perform everything with excellence. Partly complete is not good enough. So like we never do something that's like, hey, we're just gonna plug this in real quick and then we'll fix it next week or something like that. We're not gonna do something like that. Just do it right the first time. Take your time. It's okay to take a little more time if you're doing quality over just going fast, right? So in the long run, it's going to be a lot better if you do things with quality because it'll last longer versus if you try to like jerry rig things and run things really quickly. We also inspect failure points between every official competition. We make, and even matches, make sure that nothing's getting cut, nothing's getting snagged, no cables are rubbing on metal and then breaking. We inspect the wiring after every match. The other standard we have is we do not die on the field. I've said that in official capacity, we do not die on the field. So we haven't died in several years, and that's a standard that we hold, right? We take the extra time to make sure that wiring is done correctly, so then we don't die on the field. We create fail safes, so we'll wire things, we'll be extra cautious. If we have two different routes to go, we'll make sure that we spend the extra time going the one that's gonna, maintain the long life, and that's a little more safe on the cable. And then we also don't compromise on quality when it comes to wiring. So we can go to the next slide. Here's some closing remarks. So electrical should never be a quick fix. I mentioned that before. Unless you're again, need to go to a match, you need to use a Wago connector or something like that. But the thing with Wagos is Wagos are, a lot of teams, like I said, will use them permanently. So Wagos are built pretty well. It's just that over time they wear out. So Wagos are a sufficient quick fix, right? It's okay to use them for a quick match. You don't have to worry. A lot of times if you use them correctly, they're not gonna unplug during a match. But it's not something that we would use permanently. The robot should never die on the field. Our wiring diagrams need to be made from the electrical team when they wire the robot. Diagnosing is usually simple, but it can become tedious. So a lot of times when you're diagnosing the robot, it's something it's the simplest thing, right? It's like if you're dying on the field instantly, then it's something on your main line, right? It's not gonna be a motor, right? It's using logic to kind of diagnose very simply, but a lot of times it can be tedious to look through the robot. CAN bus is what controls the signal for the robot. Wires need to be fastened if you want to maintain long life and a lot more robustness. And then the battery care is critical. Maintain your batteries. All right, let's go to our first scenario. So during a match, the robot enables normally and drives for about 10 to 15 seconds before abruptly losing power. The driver station immediately reports no robot communication, and the voltage reading drops near 7 volts. After the match, the battery feels warm and tests bad replace on the battery beak, even though it was testing full voltage before the match. Here's some extra context. Robot was inspected previously, and the robot ran through pre-flight checklist, which was completely good. It worked fine. The battery was fully charged and measured at 12.6 volts or above using the battery beak. No obvious signs of damage were seen when the robot was placed on the field. After failure, the robot remained completely unresponsive until removed from the field at the end of the match. So what do we think might be a good place to start with here? Let's hear some ideas. All right, go ahead, Ben. We'll come to you, Gavin.
The connectors of the actual battery to the robot.
Okay. Yeah, that's a good start. What do you got, Gavin? Okay. Lucas?
Maybe the radio.
Okay, the radio, okay. Well, so here's what I'll say. It wouldn't be the radio because the battery is still showing, I think it says the battery shows that it's dead after the match. I thought it said that somewhere.
Battery.
Yeah, bad replace. So if it was just a radio, the battery would still be pretty much charged, right? All right, what other ideas do we have? Nothing? What?
Ryan's got one.
Oh, Ronan, what do you got? Okay, checking the age of the battery. Okay. So yeah, you guys did pretty well. So the first, there was a few things you guys missed, right? So the battery would be a good first, make sure that the terminals are tight. That's a good first area to check. The main thing to identify here is that if this is what's happening on your robot, it's something on the main line, right? That's killing your whole battery very quickly, right? So that might be the battery. That could be the battery. That also could be the connectors on the main breaker. That could be the connectors in the PDH. Something on that main cable is most likely damaged. So it could be that. It could be a sliced cable. It could be a short on the robot. Like if the insulation was vibrating on metal and then wore through. Basically, that's the first area to check is anywhere on your main line. So those 3 primary areas, but all connectors. Connection points. All right, let's go to our next one. Scenario 2. During a match, the robot is working properly, and after a large collision begins, the robot becomes hard to drive. It appears 3 of the 4 swerve modules are operating correctly and properly, but the 4th one will not rotate or drive when the controls are used. Once we get back to the pit and examine a little closely, mechanically, the 4th module is rotating completely fine by hand, and the motor is also turning, the wheels are spinning by hand when we try to do that. What might be a good area to check? All right, we'll go to Lucas because he didn't answer last time.
The wires.
What wires?
Like the wires connected to the motor.
All right, give me a little more detail on that because there's 6 wires that go in.
Like the wires that send the signal to move it.
Okay, yeah, that might be a good place. All right, what's anyone else got? Adi, what do you got?
So like if it's after the collision and just doesn't affect the wires that are connected to the motors or like the motors or
Yeah, you guys did good. So it's probably something isolated on that motor, right? So that might be like a splice in that specific can line, right? That could also be a power issue, like maybe the motor lost power, something like that, right? So and that could also be like Adi said, maybe like one of the encoders went out, and if the encoder went out, the motor would probably still rotate in the match, but it might become very hard to drive. All right. There should be one more. Yeah. Okay. Scenario 3. The robot runs well early in the match, driving smoothly and operating mechanisms without issue. About halfway through the match, however, the robot begins to stutter when multiple mechanisms are run and activated at the same time. For example, when driving and running the shooter or intake simultaneously, when running multiple mechanisms, the robot begins to stutter. When fewer mechanisms are active, the robot seems fine again. Here's some more additional context. The robot performed normally in the pit prior to this. During the match, the robot slowed down significantly under high load. And the driver station voltage chart shows dips as low as 6.8 to 7.5 volts whenever several motors are active. What might be a good spot to check first? Here, go ahead, Adi.
the main power line because
Okay.
the batteries are browning out.
Okay. Any other ideas? All right, what do you got, Ben?
Mechanisms to make sure that they're not drawing too much power for themselves.
So it could be, I guess. So here, I'll talk about that a little bit. So if the mechanisms were drawing too much power, then the breaker would trip, right? And then it would shut that off, right? So it wouldn't be a mechanism. It wouldn't be on the main line probably because it's not like it's dying instantly, right? It's only when multiple mechanisms are run. So Gavin did really well with this. It probably would be something like the battery, right? Where the battery is worn, it's an old battery, something like that. So it acts normal, but then over time with high load, like it could be a bad battery, right? That might not be charged fully. So then, like, let's say a battery's half charged. When you're using low, like only a few mechanisms, it might operate completely fine. You might be able to just drive with like a half battery or 3/4 of the battery. But then when you're activating multiple mechanisms at once and it's pulling all that power, the battery wasn't charged fully. Then you're really draining it all the way to zero about partially through the match. So that would be a good spot to check first. It might be a bad battery. I think that might be it. Okay, so here's another quick quiz. All right, so my guys who have spoken multiple times, we're gonna let you guys have second round. Okay, let's see if those who haven't spoken yet can help here. So let's name some of the components. What is that one there on the left? What is that one called? But don't call it out. Raise your hand. Oh my goodness. Don't make me redo this entire presentation. You don't want to sit through it again. Hold on, Travis. You already know. I know you know. All right, Trexler, what do you got?
Power distribution module.
Close. All right, that's close. Does anyone know the full name?
Lydia just told me power distribution hub.
Okay. Well, Lydia, you could have answered for yourself. You haven't answered too much. You could have also spoken up. That's all right. All right. So yeah, you were really close, Trexler. So it's power distribution hub. All right. This one, hopefully the easiest. What's that called? Yes, this is the RoboRio. All right. All right.
Name its use.
Oh, okay. Well, yeah, that's actually, we might go back to that. We'll see. What's this? All right, Ronan.
Radio?
Radio, okay. And what is this? All right, Adi.
The radio like power hub.
Okay. All right. And what is this used for? Oh my goodness. Come on, guys. All right, Ronan, go ahead.
Communicating with the drive station?
Okay, yep, that's a good answer. Good enough. Okay. All right, next slide. All right, what is this? Yeah, motors. All right, Michael, I would call on you, but everyone already said it. What is this? Controller. Yep, motor controller. Okay. Hopefully you know this. All right. What is this?
Matic thing.
Yeah, I accidentally didn't cover that one. Yeah, I didn't cover that one somehow. Oh, you know what? I don't know how, but okay. All right, here's a question though. What is this used for?
It's like a mini PDH powering like multiple lights.
Yeah, so it's a mini PDH, and yeah, I mean we might use it for multiple lime lights. All right. We can go to the next slide.
A lemon light?
All right.
Sensor.
Someone tell me what this is used for. All right, Andrew, tell me what this is used for. Okay, yeah, good answer. That has different voltage outputs. Okay. And what is this?
Sensors.
Okay. All right. Okay. And then this? Compressor. All right. Let's name this one. What is this? RSL, and then that one? All right, perfect. We're doing well. I think that might be it. All right, that is it. So hopefully you guys learned some things. I saw that, Dia. All right, so that's the end. So does anyone have any questions? Probably not. Okay. All right, perfect.